Hello, welcome to another exciting time. In this video, we are going to be talking about the force of interest. In my previous video, I talked about nominal interest rate, looking at how it behaves when it is convertible to maybe semi-annually, monthly, or quarterly, depending as the case might be. Now, under the force of interest, what are we going to be looking at? We are looking at the rate per year at which an investment is earning interest. The rate per year at which an investment is earning interest. So it could be a savings. We want to look at what rate is it actually earning interest, most especially when the convertible periods keep increasing. Like let's say, for example, as I said, semi-annually, it means that it's going to be compounded twice in a year. And if we're talking about quarterly, it's going to be compounded 4 times in a year. If we're talking about daily, and what particularly happened? At what rate is this interest actually bringing, is coming in based on the investment that we have? Now, by definition, we know that the annual interest rate is I, which is equal to, we have 1 plus, and I have I here with the M up here, and then I have M raised to power M minus 1. So by definition, when you check my previous video, we talked about this. Actually, this is a standard definition that the annual interest rate, when we want to convert the nominal interest rate to the annual effective interest rate. So the I, which is the annual effective interest rate, is equal to, here we have the nominal annual rate, and this is I with this notation with the M and then in bracket. So we have divided by M all raised to power M minus 1. Now M is the period. That's the number of times it's going to be compounded for all through. Like how do we compound in a year? So if we compound in the case of semi-annually, M is going to be equal to 2 because we are compounding twice in a year. If it is quarterly, M is equal to 4. So you can feel free to check my previous video and you're going to see I actually give an explanation on that. But then let's look at it. What happens when this particular value keeps increasing? Take, for example, we say semi-annually, M is going to be 2. When we say quarterly, M is going to be 4. When we say monthly, M is going to be 12. So you can see M keeps increasing when we are looking at it in terms of how many times we compound in a year. How about daily? If we are going to compound it daily, of course, M is going to be approximately equal to 365. So you can see the value of M keeps increasing. Now, of course, the value of M keeps increasing. We believe that there will be a time whereby there won't be any more significant change to the annual, that's the annual effective interest rate. There won't be any significant change. So we want to look at the behavior because, say for example, if we are to say M is going to be like the number of times we compound in a year is is convertible hourly. Now, if it's convertible hourly, of course, M is going to be 365 times 12 because we have 24 hours in a day. Now you see that M keeps getting larger. So that's what brought about the force of interest. We want to look at the rate per year at which an investment is actually earning interest. So there are two basic types we're going to be looking at today. We're going to be looking at when the force of interest is constant and then when the force of interest varies. Probably it changes. So we want to see what happens when it is constant and when it is, and then when it varies. Now, looking at this, for constant force of interest, we took all this. Now, we usually denote it with this notation. For constant, this is actually what we use, a delta for that. Now, since M is going to go to infinity, then we need to find the limit to this, actually. So I'm going to say I, which is going to be equal to, in bracket, it's going to be equal to the limit as M goes to infinity. We're looking at what about it goes hourly or it goes in terms of minutes now. So we say M goes to infinity, then 1 plus, now we have our force of interest here over M all raised to power M minus 1. Now, this is exactly what we have. That's when we are talking about the annual interest rate, looking at where the convertible period keeps it goes to infinity. So we have m going to infinity. So certainly, since this is exactly what changes, then we need to find the limit that will help us know what particular boundary it will not exceed, no matter what happens to m as it keeps going to infinity. So by definition, you would see that the limits of as m goes to infinity of 1 plus delta over m raised to power m minus 1, this particular definition, that is to say this, by definition, is same as exponential delta minus 1. So here you see that we have gotten a very important, should I call it now, model, that we can say this one goes here. So I plus 1 is equal to exponential delta. So I'm going to put this in a box. Like, I'm going to put this in this in this rectangle here. So it's a very important one for you to know that I plus 1 is equal to exponential delta. Now, this is quite familiar because we have seen something like this before. Now, when we say this also looks like, in terms of maybe, let's say, the accumulation function. The accumulation function a of t, which we know to be 1 plus I raised to power t. Now, when we plug this in here, that tells us that the accumulation function is going to be exponential delta dot t, or t dot delta, depending as the case might be. That's delta times t. So you can see this is another important model based on definition. That's when we are looking at the force of interest, when the force of interest is constant. Now, we also have the present value factor. That's the present value factor, which we denote as V. Now, don't forget, V is actually equal to 1 over 1 plus I. So you can see, same as something like this. So I can simply say V is going to be equal to exponential minus delta, because this was the same as 1 plus I raised to power minus 1. So this is another important model that we need to know. So you can use this, feel free to use this whenever you want to solve a question. And then when the question said that when the question says the force of interest is constant. So depending on what you're actually looking for, you should know that 1 plus I is equal to exponential delta, or we have the accumulation function. If you are going to make use of the accumulation function, that is a of t is going to be equal to exponential delta times the t. And then if you are going to use the present value factor, you are going to see that v is going to be equal to exponential minus d. Now, these are very important. So we are going to go back to this later on. But then, what happens when the force of interest varies? So now, by definition again, for varying force of interest, we can say delta of t, because it is a function of t. Now, remember that we said it varies, so it's a function of time. So that's why we have delta of t here. We have delta of t is going to be same as a prime of t over a of t. Now, this is by definition. So you should have that by definition. So now I want to differentiate this now. That is, I want to take the derivative of the natural log of the accumulation function. Now, when I differentiate this, what I'm going to have first, I'm going to differentiate this. This gives me 1 over a of t dot. Then when I go in to differentiate, I'm going to have a prime of t. Okay, so now I have d the t of this function is equal to this. Now you can see that it looks like this above. I have 1 over a of t dot a prime of t. So I can simply say this is equal to what I have here. So that's it, d dt of the natural log of a of t will be equal to what I have here, which is a prime of t over a of t, and that is equal to the delta of t. So I have that in here. So invariably, I can say that delta of t is equal to d over the t of the natural log of a of t. Yep. think I can say this. Yes, that's quite clear that what I have here, this is actually equal to this. Now, I will now decide to integrate. I would like to integrate both sides to find the that is the accumulation function in relation to the varying force of interest. So integrating both sides, and I'm going to take that from 0 to k, a period of time. So delta of t, the t, will be the 0 to k d over dt, the natural log of a of t, and then the t here at the end. So looking at this, you can see that we have an integral sign here, we have a derivative sign here. So that goes, leaving us with just this function. So we have the natural log of a of t, and then don't forget this is a definite integration. So we take it from 0 to k, and that's what we have. Now, when I plug this in, that simply means the natural log of a of k minus the natural log of a of 0. Now, by definition, the accumulation function, because we are looking at it in terms of a unit investment, so that implies that I can simply say a of 0 is actually equal to 1. So that makes the natural log of a of k minus the natural log of 1. Now, the natural log of 1 is 0. So that simply means I have 0 to k delta of t dt will be equal to the natural log of a of k. Now, of course, as I said, that's because the natural log of 1 is actually 0. So that leaves us, we were able to come up with something like this from 0 to k, and then we have this. Now take a look at this. Let me take the exponential of both sides. Now, taking the exponential of both sides, because to have this particular value, or rather I could put it in a better way, right? All right. Now, we came up with something like this, 0 to k delta of t, and that's equal to this. So taking the exponential of both sides, I'm going to have this exponential with the 0 up to k here, and the delta of t, the t, and here exponential, the natural log of a of k. Now, when I take the natural log, of course, I have the exponential with the natural log here, so it goes away, leaving me with this. So that makes a of k to be equal to exponential 0 to k delta of t dt. Now, this is exactly what I have. So looking at it generally, so I'm going to say in general, that simply means that the accumulation function a of t is going to be equal to the exponential of 0 to t delta of t dt. Now, this is very important. So you can see, now we have a of t is equal to what we have here. Now, this is very important. Now, that will help us to be able to solve question. That's when we have maybe, let's say, a constant force of interest, or when we have a varying force of interest, we're going to find the accumulation function. The accumulation function, a of t, is equal to what I have in here. What have we been looking at? At first, when we have force of interest, that's to say constant force of interest, which we denote as delta, it simply means that the first thing we came up with is that 1 plus I is equal to exponential delta. That is 1 plus I equal to exponential delta. We also saw that the present value factor, that's the present value factor, which we denote as V, is same as that's exponential minus delta. And then we have the accumulation function to be equal to, we have exponential, because of course the accumulation function is 1 plus I raised to the power t, so that becomes exponential minus delta, no, sorry, no, with the minus, So we have exponential delta dot t, that is multiplied by t. So this is exactly what we looked at when we say constant force of interest. Okay. Now for varying force of interest, let's say for varying force of interest, which we denote as delta of t, the first thing we saw was that delta of t is equal to a prime of t all divided by a of t. Now, don't forget, a of t is the accumulation function. So we said we're going to take the first derivative of the accumulation function divided by the accumulation function. And then the second thing we also discover is that the accumulation function is equal to exponential with this integral 0 to k, sorry, delta of t dt. Yes. So whenever we are looking at constant force of interest, we are going to bear this in mind. We have 1 plus I equal to this. We have the present value function equal to exponential minus delta. Then we have the accumulation function equal to exponential delta times t. Then for varying force of interest, we have delta of t to be equal to a prime of t over a of t. And then we have a of t to be equal to exponential raised to power what we have in here. Okay, so I'm going to solve a question now to help understand how we can make use of this problem. Okay, we have a question here. Given delta of t to be equal to 6 over 2t plus 1, find the accumulation function, that's a of t. Now we know that by definition, a of t is equal to exponential 0 to t delta of t dt. So by definition, this is exactly what we have. Now representing this becomes the exponential 0 to t 6 over 2t plus 1 dt. So what I'm going to do, I'm going to integrate this. When I'm done, I'm going to bring it back in here and then see what my accumulation function will be. At least it's going to be something in a very much simplified form. So I'm going to pick this up. So I have the integral from 0 to t of 6 over 2t plus 1 dt. So I'm going to integrate by substitution. So that means I will let u to be equal to 2t plus 1. Then I'm going to differentiate du over dt. This gives me 2, which implies that dt is equal to du over 2. That's when I have to resolve this. I'm going to have the t to be equal to du over t. So I'm going to take this and this as well. I'm going to put it back in here and then see what I'm going to have. 0 to t, 6 over 2t plus 1 dt. This becomes 6 over u, and that's because 2t is same as u, and dot y dt is same as du over 2. So du over 2. Now you see this 2 goes into 6, that's 3. And then I can bring out the 3 out of the integral sign. So this becomes 3 and then 1 over u du. And by integration, this means 3. This is 3. And I'm going to have ln u, or I can go back to introduce that, but fine, let me just have that, the natural log of u. But then this is 3, the natural log. What is u? It is 2t plus 1. Don't forget it's in an integral, so I can take 0 to t. Now, when I bring in the definite integral interval, so I'm going to have 3 into the natural log of 2t plus 1 minus the natural log. Now, when t is 0, that's 2 times 0. That gives me 0, leaving me with the natural log of 1. And of course, the natural log of 1 is 0. So that becomes 3, the natural log of 2t plus 1. Now, this can also be written as the natural log of 2t plus 1 raised to power 3. So I can have that in that way. So since I've gotten this, the whole of this integral becomes this. So I'm going to take this and plug it back in here. So I'm going to have a of t to be equal to exponential, and the whole of this is this. So the natural log of 2t plus 1 raised to power 3. Now you can see the exponential function here and the natural log here, which cancels through. So I'm going to have a of t to be equal to 2t plus 1 raised to power 3. So you can see that this is the force of interest we have here. And then they said we should find the accumulation function. So the accumulation function is equal to 2t plus 1 raised to power. You can subscribe to my YouTube channel. I'm going to be dropping lots of videos again. And then I'm going to be solving questions from the Society of Actuary Exam FM that will warrant us making use of either the constant force of interest or the varying force of interest for better understanding. Thank you very much.